start just to give you some impression of the students' performance last year. In the last year, the examination, if we counted as a 100%, which was 55.1, with the coursework 64.2, which make actual percentage 57.4. These results was significant improvement in comparison with the results the year earlier than the last year, which is the average is 50 combination of the coursework and the examination. So we wish you continue.
We will get 64.
I was just going to say, I think it's worth perhaps saying the highest mark was, I think, just short of 90. I think I remember counting something like between 13 and 15 got marks over 70%, so first class marks. I can't remember how many people got below 40.
There's a lot.
Both single figures.
So now we just go through question by question. Certainly, after this, we have the prize for the best 3 coursework you voted. So we put this at the end. Checkers inside.
Oh, funny bastard. Oh, God.
So now we come to page 1. The first question is set jointly by myself and Dr. Bell. I cover the first question 1A. You may recall that in the revision last time, I actually go through the part of the question I said. So the basic idea is that we know that strain is differentiating ones over displacement. So for the first part is differentiating. For the next part is we integrating from the strain field to the displacement field. We also mentioned that there could be a mistake about the integration constant. In this time, integration constant, if we're integrating in respect to x, the integration constant is a function of y. Okay. Also, we ask you to mention the features of each of the 2 elements. This element 1 is 8-noded elements, because you can see from the equation, and another one is 4-noded elements. So in the handout you receive, we mentioned in the class, you can easily find out the features. Finally, sometimes the students not draw this very correctly, is that we have 2 elements. One is 8-noded, one is 4-noded. This is coming to question 1A, 5. Draw the likely deformed shape of the element when subject to Q bending. In other words, we put the bending moment here. For this element, because it is 3-noded, so it can deform in a parabola. For this one, because 4-noded, the deformation only can be straight line. So this is the deformation is the element allowed. This is 2 regions. You may recall your fitness element analysis. When you use this element, the displacement you calculated is smaller than it should be. Any question for this part?
Yes, one.
On the left one, is it the side straight or cement?
For here,
Yeah.
it's straight. This is more like a beam. For beam, we have an assumption when in bending, the plane remains plane after bending. So, by the way, it can be curved, but in this case, there is no need for curve on this side.
Okay, the second bit of that, the first bit, just really was straight out of the notes, and it's really just to demonstrate how the method of virtual work can be used to produce an influence line. So it's a diagram and about 2 lines of calculation, but directly what's in the notes, and that was worth 5 marks. The next bit was this structure here, and it asked for the influence line for a shear force of D, V rather, and a bending moment of B. So that's the sort of thing that we've been doing in the last couple of lectures. It wasn't particularly well done, that. I think a number of people just didn't get around to doing the first bit, so that's a loss of 5 marks. And then possibly some errors crept in on the other one. In fact, there were 16 marks, I think, available for that, and the average mark was only about 7. So not really so good on that. Highest was 16, some people got 4 marks, and some people got the opposite end. So that was that whole question. Second question was what I said, which revolved around that structure there. The first bit asks you to derive the member stiffness matrix for a member with 1 end pinned, and the transformation, and for a member with 2 ends pinned, and the transformation matrix. That's really pretty much straight out of the notes. What we give you are those standard diagrams. From the standard diagrams, you can work out what happens when 1 end of the member is pinned. What you have to do would be with the 2nd, the 3rd, the 5th, and the 6th that have moments at that end. Get rid of the moment, apply a moment in the opposite sense, carry over half to the other end, and then you've got moments there. It is in the notes. Some people simply remembered the member stiffness matrix for that. And if you could remember it and get it right, I would have given some marks for that. But it did say derive, and if it says derive, that means you've got to explain where things come from. So some people would have lost marks simply because they didn't derive. That sort of seems a shame. But then it was just a question of going on and doing this structure. If you've got the member stiffness matrix, remember with the right hand end pinned, that's what you need for that. The little x, the big x-axis is the same. There's no transformation required. Just bang the numbers in there. The pin end, remember, that's only a 4x4. Sorry, a 2x2. It starts off and goes into a 4x4. But there is a transformation there. If you take that as end 1, the angle for the transformation is that one. If you take that as end 1, the angle is that. It goes on and asks you to get the equations that would be solved to get the unknown displacements. So that's effectively the displacements of this joint here. So there are just going to be 2 of them, the x direction and the y direction. So it's 2 equations. The total for the structure would be 3 plus 2 is 5 plus 2 is 7. But you only need to get the 2 that relate to that. Quite a lot of people would be able to set up the matrix, and sort of comes in the form, doesn't it, that you'll have something in there, stiffness matrix in there, and it'll be XC, I think, and YC in there. To complete it and get the full marks, you need the numerical values that go in there. A lot of people able to do that because the mechanical process, but they miss out on that. And that really is quite easy. It's just a question of finding the effect of this force over here and the effect of that moment over there. The moment perhaps might make one think a little bit. It goes like that. So to resist it, you're going to need reaction forces like that. This one here can be turned into horizontal and vertical components, and what you actually need over in here are the opposite of these two forces. So they would be the member forces from that loading. You add it to what comes from that. So again, people lost marks, so they didn't actually do that bit. Then goes on and says, determine the vertical deflection B, that was this point here. So that means solve those two equations. It's only two simultaneous equations, so that should be fairly straightforward. And then get the value of the bending moment at A here. Remember, if you do it from the member equations, you have to add back the fixed end moment that arises out of that. So quite a lot of people probably wouldn't have attempted that last bit. To actually do it, it's about 4 or 5 lines of calculation, that's all, maybe less even than that. So, you know what you're doing, it's very easy, but often people seem to stop with the mechanical bit of just getting that. So I would just urge you to go on and look at that and the last bit, because they're easy, they're short, you know what's going, it's much easier to get marks on there than the flogging through you have to do to get that. I think that was the most popular question on the paper. More people did that than any other single question. The average mark for that was somewhere between 17 and 18 out of 33. So around about the average for the paper, I guess. The highest mark, nobody got full marks. The highest mark was 27.
Would it just be 20?
The lowest mark, well,
What's our distance there? About 5
okay,
times.
and then
5.
the second or the third
Oh shit, battery.
second forward bicep
Pythagoras, you work out the distance and work
revolves
out
around this structure.
Yeah,
there.
okay. So you got addition.
First
Get
part
just resolve it.
said
Get
and
the
once you resolve it, just give them opposite sign.
half.
Yeah.
So that's using an energy method. I think when I did my solution, I used Castigliano, which is du by v is equal to delta. Fair number of people did that. You could, though, use the virtual work method if you want. And that's the integral of m1 mp over d by dx is delta. So either would have been fine. And people did use both methods. Second part of the questions went on and said, okay, suppose we change the fixed support to a plate and add a prop or a tie down in there. And what it asks you to do is just something to do with change in deflection. Determine the value of the area A, of this member here, if the deflection isn't changed by more than a set amount. So again, it's tantamount saying, what's the deflection of this point here? So, main structure is the same. How would you do that? Again, you could use Castigliano, but now you'd also have to assess the strain energy in that member as well. But it's only an axial one, so that's just an extra term. Turns out in computing the strain energy, because now you've changed the structure with the support there a bit, but it was done in such a way that the equations you end up with, either whether you use that or you use that, actually look the same. There's a change in sign of one term. So any work you've done on the equation in the first part, you could use directly in the second part. That 46 people did that, so it certainly wasn't the most popular. I think it had one of the higher averages on the paper. The average mark for that was getting on for 20, so a higher average than the stiffness one, but fewer people doing it. And I think often that sort of says, you know, somebody's checked, they've got grips with the energy methods, and if they've done that, then it's a fairly straightforward question. The highest mark for that, I think, was full marks for that one. And the lowest mark was above 0, so it was quite good. On either of those, any sort of general questions or observations anybody would like to?
Did you know how to do this?
do hope you have a
Let's
go
look at it.
them.
If you say simple.
Any problems you
It's
have a
not
go at,
simple, it's just...
let me have them. I'm very happy with them. Quite a few people are giving me them now.
Dikara told you I need to go to the exam papers, go ask me those fucking questions again.
Usually try
Where'd
and
you
do
do
it in
this?
about 24 hours. We get a lot at one time.
I want to do it, you know that.
Okay, that's my...
So now we come to question 4. In the revision, we have done a coin question a few weeks ago. And in the revision, we have to see all the structures for question 4. So once again, you see the patterns of a question are very similar, while the structures is changed. A few students visited me already. What they stuck is two things. One is what's the free body diagram, how to show the force, the likely deformation, and also possibly the calculation. So now is put here is the free body diagram. So we say we cut upper right quarter. We cut here. The free body diagram, it means that we leave all the actions on the structure. First is that we copy the loading. Now we look at internal force. We know that a force is here because this line are not in the left or the right. So there must have a force here. So how the force distributed, we may not so clear. So the first is that there must have a horizontal force. There must have a bending moment. Why there have a bending moment? Because this force, is coming to the middle. This coming to the middle. These two forces equilibrium in the horizontal direction, but there are a couple. So there must have a moment. Now we look in this direction. There are no force here. So the vertical force in this line should be equal to 0. However, there may be a bending moment. In other words, if there are possibility, the forces in this way, half positive, half negative, which cancel each other. So actually, we don't know there are any force. So for this direction, we know this force is equal to 0 because there are no force here. And also, we come to m is equal to 0. Otherwise, we cannot do the calculation. At the end of a question, you are given the opportunity to say the possible modeling error. For this diagram, it's very easy for calculation of the normal force and also the bending moment, which generate the stress distribution like this. Then you add up. Regarding to the deformation, the likely deformation, we can judge that. We need to judge it in such a way there are no deformation on these two lines due to the condition of symmetry. Even move either to the left or the right, it's against the symmetry. So to deform the shape, so from here, these two lines not deformed. The load applied here provide a push. There are possible deformation. This is deformation is allowed. This is just a qualitative indication. For this age, there are no constraints. It's allowed deformation. if you squeeze a rubber in one direction compressed, another two direction will expand a bit. So this is, you can logically we put little something here. So for the deformation, there may be a little move inside. This is the likely deform the shape. Any question? For calculation, this time I think this question in terms of calculation is easier than the coin example, where we need a bit of integration to calculate the force which along the edge. This is just a very straightforward calculation using the equilibrium conditions. Any question? So, for this equation, the average is 18.2. Second least number of students take the equation, which is 54. So once you know that the question pattern is very similar, you just need to also raise straightforward. Is it plane stress problem or plane strain problem?
Yes.
Yes,
Stress problem.
Very dominant. Okay. So now we come to the next equation. The first, there are one question divided by several sub-questions.
Where's the microphone? My phone.
First one is to show the force path. To identify force path, actually, to identify the members that have no zero force. In other words, they are not zero force members. So if I draw the force path, I give you the example here. The force path, how the load is transmitted from the members to the support. So we can sense that these members have forces.
Just like you.
The force goes this way to the support. In other words, the member with dashed line, they are not zero force. For other members, they are zero force. So in this way,